Okay, so in LDA we make a further assumption than the fact that the class conditional density is Gaussian. So what else can we assume? So I am going to assume that sigma k is the same for all the classes k. So what does that mean? It means that I will do that in 1D, right. If it means that, so class 1 could have the mean of my Gaussian here, class 2 could have the mean of the Gaussian somewhere else, right. But when I look at the right, so that is the same, right. All I can do is shift the Gaussian around, but I can't change the shape of the Gaussian. Okay, is it clear? When I say sigma k is the same for all the classes, it essentially means that I can just shift the Gaussian around, I can't change it. So in 2D it will be like, okay, let's assume that that is the equivalent of 1 sigma contour, right. If that is the case for one class, right, for the other class also it has to be similar. Okay, so I can't have one class looking like this and the other class looking like that, right. Does it make sense? People are able to visualize what I mean? Can you see that at the back or at the on the TV there, right. So it has to be that both the classes look similar, right, in terms of the variance. Okay, that is essentially the assumption we make here. Okay. So in looking at logistic regression, we saw that we could look at the log odds, right. So likewise I am going to look at log of right. So when I am at the class boundary, what will this ratio be? 1, right, and log of that is going to be 0, right. So I can actually solve for this ratio equal to 0 and I can get my boundary, right. So now we know what is the form of probability of g equal to k given x, right. Now I can put it in here and I can solve for what? Yeah, but what are the parameters I should be solving for? And mu and sigma and anything else? We are talking about this, so we have to solve for pi as well, right. And solving for pi is rather straightforward, right. I mean, you just count the number of data points that belong to a class, right, divide by the total number of data points you have, that gives you pi. Okay, so it is not like it's complex, but you still have to solve for it, right. It is not that it is given to you a priori, so you have to estimate pi from data. So all these 3 parameters you have to estimate, right. Yeah.
Why are we looking at the probability of that data point belonging to a different class in the denominator?
Yeah, so this gives you the boundary, right. So when the probability of it belonging to k is higher than the probability of it belonging to L, then you will put it in k, right. So you will have to do this for every pair of classes to make sure that you have the right class. So assuming there are only 2 classes, just you have to make one comparison, but suppose there are really k classes, you will have to make k minus 1 comparisons for to figuring out which class it belongs to. So this essentially will give you the boundary. So when the probabilities are equal, then you know that, well, it could go either way. So this is going to be 0, right. So when the when it actually belongs to class k, the numerator will be higher, when it belongs to class L the denominator will be higher. So based on that you can decide which side it is going to go, okay. Yeah, so what about now solving for this? This is essentially log of right. So the denominator will get cancelled out, right. You only worry about the numerators in the thing, right. And the fact that we assume that the variances are the same is also going to allow us to cancel out a whole bunch of other terms. So what other terms can cancel out? That can go, right. So this has sigma k, it will become sigma. So when I take the ratio of the two things, this thing can go, right. So I do not have to worry about that. And this log and there is a e, right. So all of that will go away. Right. So roughly the way to think of it is, if I had taken out the product here, right, if you think of the term by term product here, right. So I will have some terms that will have an x squared, okay, some terms that is going to have x mu, okay, and some terms that will have mu squared, right. So when I am taking the ratios, I am going to get mu k squared minus mu l squared, right. So that is essentially what I am writing out here. The first term here corresponds to mu k squared minus mu l squared, right. So you have to get familiar with doing this in the vector notation, that makes life a lot easier. I am just giving you the intuition here, if you can write it out and see that this is the right way to simplify it, right. So if you think of this, essentially you are going to have a x squared term, mu x term and a mu squared term, and when you take the ratio, so you will have e power this divided by e power something else, so that is going to become minus mu in the numerator. So you are going to have mu k minus mu l squared, right. So that is essentially what I am writing out here. And you have your, what about your x squared terms? X squared will get cancelled out because sigmas are the same, right. So sigma k and sigma l is the same, so x squareds will get cancelled out, so I only have the x terms left, right. That is basically it. Right, so I will have x mu k minus x mu l, so I am going to get that term as well, okay. Okay. Yeah. It is actually plus, okay. So it turns out that this separating hyperplane that we have, this is essentially the, solving this for 0 gives us the separating hyperplane. The separating hyperplane turns out to be linear in x, right. I mean the separating surface turns out to be a hyperplane, right. Separating surface turns out to be a hyperplane. That's the way I should be saying it, yes. Right, so to get the linearity we needed to make this assumption. If we do not make this assumption, so what will happen? The x squared term will stay there, right, and what we get is QDA. I told you about QDA, right. So if I do not make this assumption I will get QDA, right. Something more. So I said in discriminating function case we always have some function like this delta k of x, right, and if delta k is greater than any other delta L, then we will classify the x into k, right. This is what we said was the idea behind discriminant functions in the very beginning. So what would be the discriminant function version of LDA? Right. So please note that for most of this part when I am writing sigma here on this side, okay, it is covariance, okay, and I will make sure I write limits whenever I write the summation sigma, just for whenever we use multivariate Gaussians, okay. So I knew I left out one somewhere, yeah. Okay. So this is essentially the discriminant function, right. So you can just compare this, and this is whichever has the highest discriminant value will become the class, right. So pi hat, like I said earlier, you count the number of data points in the training data that belongs to class k divided by total number of data points, you get pi hat k, and mu hat k, you pick out all those data points for which the class was k from the training data, find the center of them, that gives me mu hat. That makes sense, right. So what about sigma? What's that?
Writing pi k and mu k.
Pi k.
Assuming that you have a large number of data.
Well, presumably so, because these are all data points that belong to one class, right. Right. So when the training data comes, I am assuming that I have sufficient number of data points of each class. Otherwise, I won't be able to learn anything.
This won't work if you have a small data.
It will work to the extent possible with a small data set, right. Suppose I give you only 10 data points for training, okay, then you are anyway in soup, right. Most of your parameter estimation algorithms will not work if you have very little data. There are some class of algorithms which work with very little data, right. So one such thing which we will look at depending on time today or tomorrow is a support vector machine. So it works with very little data, but most of the other parameter estimation methods require you to have some amount of data, right. Yeah, so what do we do with the variance? So remember that variance is not limited to the class, okay, it is across all the classes we really want the same variance. So essentially we do what is called a pooled estimate. So we essentially use all the data points for estimating the variance, not just the data points belonging to one class, right. But then what is variance? Right. So that is variance, right. You add that up and divide by -1, right. So remember that you always do a -1 for variance estimates, school stuff, right. You given a sample mean and sample variance, you must have done all of that, right. Sample mean is add up the data points, divide by n, and sample variance is data point minus mu squared divided by n minus 1 usually, right, to adjust for the fact that mean is a dependent variable on all the data points. Okay, so the n minus 1 essentially gives you an unbiased estimate of the variance, right. But then what is the mean you plug in here? The mean corresponding, okay, so the mean of mean is a bad idea. No. So no, I don't. Thanks for bringing it up, because that is a natural confusion when I say you are going to estimate the variance across the entire population. So the natural mean you are going to plug in is the mean of the mean of the whole data, right? But that is not correct. Why? Because I unfortunately rubbed the picture, but I am only worried about the variance within the class, right? So I should plug in the mean here of the class of xi, right. Remember, all of this is from the training data, so I know what class xi actually belongs to, right. So I take the class of xi, so I assume I will take all those data points belonging to class k, and then I will use mu k here in computing this quantity, right. Then I will do this over all classes. I will do this over all classes, and then I will divide by k. That is capital K, okay. So I will divide by n minus k. So this is a slightly different way of doing the variance as opposed to computing the variance of each class and taking some kind of a mean, right. This gives you a slightly more robust estimate of the variance, okay. So this is called a pooled estimate, and right, great. So if you think about, let us say I have 3 classes that look like that, right. So this will be somewhat the separating surfaces that I will learn, right. If these had been completely spherical, if this had been like this, then the separating hyperplane would have been perpendicular to the line joining the means, okay. This is something which I just want you to note, right. In fact, I can ask you to show that it is fairly straightforward on univariate Gaussians, but if it had been spherical, it would have been perpendicular to the line joining the means, because I have now, this is slanting, right. So this will also be the separating hyperplane will also be at an angle to the line joining the means, okay. Fine. Any questions so far? So if you look at many pattern recognition textbooks, right, they will talk about LDA as a feature selection mechanism, right. So you remember we looked at PLS when we did regression, right. So we did principal component regression, where we said we are looking at the directions in the input, only taking into consideration the input. Right. So where we are looking at the direction that maximizes the variance in the input, and then when we did PLS we took into account the class labels as well, right. So the equivalent of that in classification is LDA. So you can think of LDA as actually finding directions along which the variance between the classes is maximized, at the same time minimizing the variance within the classes, right. So PCA just maximizes the variance of the data, right. LDA maximizes the variance between the classes. How does it achieve that? It tries to find a direction such that the means are as spread apart as possible. The mean of the data, right, of each class is as spread apart as possible, right. So in this case, suppose this is the mean and this is the mean. I am choosing a that's bad, right, but I am choosing some direction where the means are as spread apart as possible, right. So this is essentially the idea behind LDA, right, and we will just take that as our assumption.